Is it possible to control the speed of radioactive decay? We would very much like that to be possible because it would open truly impressive prospects for us in a wide variety of fields. And now, two American scientists, Benjamin Jones from the University of Texas and Joseph Formaggio from the Massachusetts Institute of Technology, claim that they know how this could be done. They published their method of controlling the rate of radioactive decay in the journal Physical Review Letters in September of the year 2025. Why would it be so cool to have the ability to control the speed of nuclear decay? Let me give the simplest example. An ordinary banana contains about 200,000 joules of energy stored within the nuclei of atoms of the radioactive isotope potassium-40, which makes up approximately 0.01% of any amount of natural potassium. Potassium-40 is a beta radioactive element. From time to time, one of its neutrons turns into a proton, emitting an electron and an electron antineutrino, as well as releasing a certain amount of energy. The energy released by the decay of all potassium-40 atoms in an ordinary banana would be enough, for instance, to lift a 1-ton load to a height of 18 meters. And if all that energy were to be released spontaneously, the banana would explode like a grenade. However, bananas do not explode because the potassium-40 they contain decays extremely slowly. The half-life of potassium-40 is 1.2 billion years. That is how long it takes for half of the energy sealed inside the banana to be released. In other words, for example, over 1 year, only about 5 times 10 to the power of -5 joules of energy is released in a banana as a result of radioactive decay of potassium-40 atoms, an insignificantly small amount. Therefore, bananas or even pure potassium-40 are completely unsuitable as energy sources. If we imagine a hypothetical power source based on such fuel, its total energy reserve would be large, but its power output would be miserable. But if we could control the decay rate, everything would be entirely different. We could make the nuclei of radioactive elements release energy at the speed we need, rather than at the pace determined by nature, and thus use radioactive isotopes as highly energy-dense fuel. In the complete beta decay of 1 gram of potassium-40, about 10 to the power of 9, that is, roughly 1 billion joules of energy are released, which is equivalent to the energy produced by burning approximately 40 liters of gasoline. If we could freely control the decay rate of potassium-40, then a standard small battery powered by 1 gram of accelerated potassium-40 could operate without replacement for about 100 years. The total reserves of potassium on Earth are estimated at roughly 5 times 10 to the power of 17 tons, giving the planet's potassium deposits an overall energy capacity on the order of 10 to the power of 29 joules, enough to sustain humanity's current consumption rate for 100 million years. A practically inexhaustible fuel source, and moreover an environmentally clean one. The product of radioactive decay of potassium-40 is stable, that is, non-radioactive calcium-40. By the way, let us talk about radioactive waste, the material we now have to store for long periods of time under special conditions until the radioactive isotopes decay naturally. If we could accelerate the rate of decay, we could simply burn out this waste artificially, making it safe within a much shorter time frame. In other words, if we learned how to control the rates of nuclear decay, we would trigger a revolution in nuclear energy. That is why scientists have spent decades searching for a way to achieve this. The rates of radioactive decay have been measured at different temperatures, in different chemical environments, and under electric and magnetic fields of all possible configurations. Yet no noticeable effect was ever observed. For this reason, the very idea was considered impossible until now. The method proposed by Benjamin Jones and Joseph Formaggio for accelerating radioactive decay. Essentially, according to their theory, to accelerate decay, it is sufficient to bring the radioactive material into a state known as a Bose-Einstein quantum condensate. We have already mentioned this unusual state of matter in our video, where we talked about various exotic phases of matter. But let us now repeat the most essential part. In quantum mechanics, it is impossible to determine the exact position of an object in space. It appears, as it were, smeared out within it. At best, one can define a certain region in which we are most likely to find the object when we perform a specific measurement. The scale of this uncertainty, roughly speaking, the size of that region, is characterized by the de Broglie wavelength of the given object. The de Broglie wavelength of an object, in turn, is equal to Planck's constant divided by the particle's momentum, or, equivalently, to the ratio of Planck's constant to the square root of twice the product of the particle's mass and its kinetic energy. From this it follows that the de Broglie wavelength, and thus the uncertainty in a particle's position, increases as its mass and kinetic energy decrease. We are talking about atoms of a radioactive substance, and their kinetic energy is simply the kinetic energy of their thermal motion. But as we know, the kinetic energy of thermal motion is nothing other than the temperature of the substance, up to a proportionality constant known as Boltzmann's constant. Therefore, from this formula it is clear that as temperature decreases, the uncertainty in the positions of atoms in space increases. And if we cool the material sufficiently, this uncertainty will become comparable to the linear size of the body itself. In this situation, we lose the ability to determine the position of any specific atom within the body. The atoms of the substance become indistinguishable from the standpoint of an external observer, and the entire body ceases to be merely a collection of separate particles. It becomes a single quantum mechanical object. How could the transition into this state accelerate radioactive decay? Let us look at what the probability of decay would be for a single radioactive atom out of n atoms in a given body. In the usual case, when atoms exist independently, their decays are separate events, and the probability that one of them will decay is simply the sum of the decay probabilities of each individual atom. In our case, all the atoms are identical, and the probability of decay for each one will also be the same. Let us call it P0. Since we have n atoms, the probability that one of the n atoms decays will then be equal to n multiplied by P0. The decay rate of a piece of radioactive material is proportional to the number of atoms in that piece, or equivalently to its mass. This is the classical law of radioactive decay, which is used in atomic and nuclear physics. However, nuclear decay is a quantum mechanical process, and in it the key quantity is not just the probability itself, but rather the probability amplitude, a complex quantity from which one obtains the actual probability of a given event by squaring that amplitude. Under ordinary conditions, all atoms exist independently, and we can calculate the decay probability for each atom by squaring its corresponding amplitude, yielding the same familiar formula of radioactive decay. But in a Bose-Einstein condensate, the situation is entirely different. We no longer have separate atoms. We have a quantum condensate, a single quantum mechanical object. And here we can no longer treat the decay of each atom individually. Instead, we must first sum the amplitudes of the decay probabilities for all the atoms, and then, to obtain the total probability, we square that total amplitude. Obtaining the probability that some atom in the condensate, though we cannot say which one, will decay. In other words, for separate atoms, the total probability is equal to the sum of the squares of the amplitudes, whereas for a quantum condensate, it is equal to the square of the sum of the amplitudes. And the square of a sum is always greater than the sum of squares. Simply put, the probability, and therefore the rate, of decays in a quantum condensate will, or at least should, be higher than in the same material in its ordinary non-condensed state. In their work, Jones and Formaggio present the following formula for the half-life period of a radioactive Bose-Einstein condensate as a function of the half-life period of the isotope in its normal state. According to their calculations, the half-life of 1 million atoms of rubidium-83 in the condensed state decreases from 86 days to 148 seconds. The decay rate increases by approximately 50,000 times. And the main beauty of this idea is that you are not merely accelerating the decay by a fixed factor. You can literally control the decay rate by increasing or decreasing the number of radioactive nuclei in the condensate. It is very much like making a fire burn more intensely simply by throwing in more wood. It all sounds simple and highly convincing in theory, but in practice, implementing this scheme, even just to check whether Jones and Formaggio have done their calculations correctly, turns out to be extremely challenging. The procedure of bosonic condensation itself is technically extremely complex. The substance must first be evaporated and then placed into what is called an optical magnetic trap, After that, it must be cooled to ultra-low temperatures, only a few millionths of a degree above absolute zero. This is usually done using the so-called laser cooling technique, which in itself is a very interesting technology. As you can see, even this process alone is already far from simple. But in our case, the challenge is even greater, because in order to achieve accelerated decay, we need a Bose-Einstein condensate of extremely high quality. A single-mode condensate without internal disturbances, flows, or vortices that break the overall particle balance or symmetry. To obtain such a condensate, we must achieve even lower temperatures, down to billionths of a Kelvin, and also implement special mechanisms for hydrodynamic stabilization of the condensate and similar measures. And if we recall that we are dealing not just with ordinary atoms, but with radioactive atoms, the problem becomes even more complicated. The issue is that radioactive atoms will continue to decay even during the process of condensate formation. And these decay events will interfere with condensation, at the very least because the released energy will heat the condensate, destroying its delicate quantum coherent state. But that is not all. During ordinary beta decays, for example, when one of the neutrons in a nucleus turns into a proton, or one of the protons turns into a neutron, additional particles are emitted, electrons or positrons, as well as neutrinos or antineutrinos. These secondary particles create further difficulties because they introduce mechanical disturbances into the structure of the condensate, disrupting its homogeneity. Jones and Formaggio proposed to bypass this problem by using a special type of beta decay, the so-called electron capture, during which one of the protons in the nucleus captures one of the electrons from the atomic shell and turns into a neutron. The only particle emitted in such a reaction is a neutrino, which leave the condensate without significantly disturbing it. The only remaining issue is the heating of the condensate due to the energy released in the decay, a much simpler problem to manage. For this reason, in their proposed future experiments to test their theory, Jones and Formaggio suggest working specifically with isotopes that decay predominantly through the electron capture mechanism, such as rubidium-83. This could indeed solve the problem, but in a sense, it also limits the idea's universality, because electron capture is a relatively rare form of beta decay, observed only in a small number of beta radioactive isotopes. To be more precise, it occurs in many isotopes in principle. Potassium-40 can also decay via electron capture. But in that case, this channel accounts for only about 10% of all decay events. In all the remaining 90%, the decay proceeds with the emission of electrons that would destroy the condensate. Thus, even if experiments confirm that the principle proposed by Jones and Formaggio truly works, it will not be possible to apply it to arbitrary beta radioactive isotopes until we find a way to prevent the condensate from being disrupted by the electrons and positrons released in such decay processes. However, even if the method proposed by Jones and Formaggio proves to work experimentally for only a small number of isotopes, that alone would already represent a colossal, fundamental breakthrough in our understanding of nuclear physics. The very first case in which humanity would truly be able to control the rate of nuclear decay. Yet even within such narrow limits of applicability, the effect of accelerated beta decay in a bosonic condensate would have not only academic, but also practical significance. In their paper, Jones and Formaggio, for example, proposed to use this effect to create powerful, directed sources of neutrinos, which they somewhat loosely refer to as neutrino lasers. From a physical standpoint, such devices would not be true lasers in the strict sense, although there is, of course, an external resemblance. Both involve the formation of intense, highly directional beams of particles. Only in ordinary lasers, those particles are photons, while here they are neutrinos. Neutrinos, or antineutrinos, are emitted in every act of beta decay. And if we accelerate this decay, say by 50,000 times, then the number of neutrinos emitted per unit time will also increase by about 50,000 times. But the most fascinating part is this. In the case of beta decay occurring within a Bose-Einstein condensate, these neutrinos should not fly out randomly in all directions, but rather form a relatively narrow directed beam, and this happens without any additional effort on our part. Why does this happen? Without delving into the mathematics, we can try to explain it in simple terms. Under normal conditions, the decay of each nucleus is an independent process in which the direction of the emitted neutrino is chosen randomly. The emitted neutrino carries a certain momentum, and accordingly, the atom that forms as a result of the decay receives an equal and opposite momentum. Under ordinary conditions, where atoms exist independently, this has no effect on the behavior of other atoms, and they too will decay, emitting neutrinos in random directions. However, in a quantum condensate, the situation is quite different. Here, all atoms are mixed and behave collectively. This means that when one atom in the condensate gains momentum in a particular direction, that impulse affects the entire condensate as a whole. The direction in which the first neutrino of the decay chain flies out becomes a special, preferred direction for all the other atoms, and most likely, they will also emit their neutrinos in roughly the same direction. This does not mean that all the neutrinos will necessarily travel exactly that way, but we can expect that the majority of them will, producing a concentrated beam of neutrinos traveling along a specific direction. I should note that in the paper we are discussing today, the part concerning the directionality of the neutrino flux emitted by a beta radioactive condensate is not rigorously proven, unlike the acceleration effect itself, which is supported by detailed quantum mechanical reasoning. Nevertheless, it is highly probable that such directionality would indeed occur. Similar collective effects have already been observed in related phenomena. For instance, in electromagnetic superradiance, also known as the Decay effect. In that case, radiation from a system of coherently coupled atoms suddenly became highly directional and coherent without any external effort on our part. True, that phenomenon involves electromagnetic radiation and beams of photons, while here we're talking about beta decays and beams of neutrinos. Yet the assumption that similar principles could also apply to neutrino emission is by no means unfounded. And if it turns out to be true in practice, if we really learn to generate powerful, directed beams of neutrinos through quantum condensation of radioactive substances, that alone would be a major scientific and technological breakthrough. First of all, it would allow us to make significant progress in the study of neutrinos, whose mysterious nature remains one of the great puzzles of modern physics. Neutrinos interact with matter extremely weakly, which makes them extraordinarily difficult to detect and study. We already know how to register them by recording the exceedingly rare collisions between neutrinos and ordinary atoms. But to do that, we must build truly enormous experimental facilities. Vast tanks filled with detection material and equipped with ultra-sensitive instruments capable of catching the tiniest bursts of energy from those rare interactions. Even such monumental installations manage to record only a minute fraction of all neutrinos passing through them. So collecting enough data for meaningful analysis can take years, and the reliability of the results still leaves much to be desired. But if we could create powerful and directional beams of neutrinos and aim them directly at our detectors, it would be a completely different situation. The probability of any single neutrino interacting with matter would remain tiny, but the number of neutrinos would be vastly greater, and therefore the total number of detectable events would increase dramatically. That would allow us to advance far more rapidly in studying neutrinos, whose true nature still hides many mysteries and provokes intense debate in the scientific community. In the longer term, neutrino lasers could also have practical applications. Because neutrinos possess an exceptionally high ability to penetrate matter, they could be used to scan massive objects and reveal their internal structures. For example, to peer deep into Earth's crust in search of mineral deposits or underground water sources. Moreover, powerful directed neutrino beams could serve as communication channels with objects unreachable by ordinary radio waves, such as underground facilities, submarines operating at great ocean depths, or spacecraft hidden from direct line of sight, for instance, on the far side of the moon. Thus, even the limited form of nuclear decay acceleration that could be practically implemented according to the method proposed by Jones and Formaggio may find valuable real-world applications. Yet the most important aspect of their work is, of course, its fundamental theoretical significance. The very fact that the rate of nuclear decay could be controlled would mark a true revolution in our understanding of atomic and nuclear physics. That is why it would be highly desirable for the theoretical assumptions of Jones and Formaggio to be tested experimentally as soon as possible. And I truly hope that among experimental physicists there will be those willing to take on the challenge of performing such an experiment. In our upcoming videos, I will continue introducing you to new theoretical studies that allow us to look at familiar and well-known physical phenomena from new and unexpected perspectives, and to find fresh practical applications for them. And if you enjoy what we do on our channel, please consider supporting our work by becoming a sponsor, either here on YouTube or through our pages on Patreon or Boosty. The link to the latter, as well as the corresponding QR code, should now be appearing on your screens. A huge thank you to everyone who already supports the project, and to all who choose to join our community of physics enthusiasts today. That is all for now, my dear friends. Take care, and see you very soon in our next videos.